Hello all. We will continue today with our buck DC example, and we will have a look to dynamic behavior. So let's start. Well, when we talk about dynamic behavior, we are actually looking most of the time to what is happening with the output voltage when we have a step load. So we have a sudden change in the load current. So since we already designed our buck converter with voltage mode control, what I did in the simulation file, I replaced the load resistor with a current source that will actually generate the step in the output current or in the load current from 1 amps to 2 amps and back with a slew rate of 1 microsecond or 1 amp per microsecond in the end. So this change from 1 amp to 2 amps and back from 2 amps to 1 amp will happen in 1 microsecond. Okay, this VSAT attribute instructs the current source here not to draw the full current until the voltage across it reaches 4 volts. So it will behave closer to a real electronic load, let's say, like this. And I also implement here for the operational amplifier a ramp for the reference voltage so that we have a kind of a stop start. So let's see how the simulation results look like. Well, you can see that in blue actually we have the current on the current source, yeah, as is replacing the load resistance. We have those very sharp edges, so it goes from 1 amps to 2 amps and back. In red we have the inductor current, and we see that it is centered to 1 amp for this time interval, and then it goes to an average current of 2 amps and then back to 1 amp. In green we have the output voltage. So here, for instance, we can see the effect of the soft start. So the output voltage is rising with a given slope. It seems that the 5 milliseconds what I imposed on the simulation, it's a bit too short, because this overshoot we have at startup is above the 250 millivolts, what we have as a requirement for the voltage transients. So that means we need to increase this to stay below. And here we have a detail of the output voltage with the undershoot and overshoot during the load change. So we know that we have a maximum limit of 250 millivolts, and we can notice that we have around 200 millivolts, or here slightly below 200 millivolts. And that's because if you remember from previous video or videos, we have a bit more capacitance that was needed. Okay, we can also switch to this. So actually this is the simulation. I can run it. Okay. Yeah, I don't know what's happening. Maybe if we try to come on. Okay, output voltage, then we can have the load current and inductor current, and we can also plot actually that's it. We can oops, sorry, we can look at the details. So here you see the load current is yeah, slowly rising, as the output voltage is rising, and here at 4 volts we are reaching the 1 amp. So this is the electronic load behavior as I was talking about. Okay, so we can have maybe a detail here. Yeah, we have this about 200 millivolts, so everything is as expected. Let's go back to the presentation file. Good. Then we want to check what is the open loop response, so checking the border plots in those two situations. So we are talking about this step load. I call it CCM to CCM. This is because in the we can also check it from the simulation. Moment, this one and this one. So we can see here that even for 1 amp load current, we are still in continuous conduction mode. So this is the red trace is the current to the inductor. It never reaches zero within one switching period. So we are in continuous conduction mode. So continuous conduction mode to continuous conduction mode case. So here are the two body plots. The red trace is for the 2 amps output current. The blue one is for the 1 amp output current. The current source or the load resistance is higher in the 1 amp case. That means the damping of the LC network is not that big, so we have a higher peak here. But we see that in principle we have nearly the same or almost the same cutoff frequency, close to 10 kilohertz, what we are targeting, and the phase margin, which is 60 degrees or even a bit higher in the 1 amp case. So we are all good here. Now let's see what's happening if we actually do this step load, but moving or making the converter to change the operating mode. So we will therefore keep the same change in the output current as 1 amp, and we will change the output current from 0.2 amps to 1.2 amps. Again, with the same slew rate, so 1 amp per microsecond. What we can notice immediately is that we are actually out of spec with the undershoot and overshoot. So we are over 250 millivolts, what we are targeting as the maximum deviation in output voltage for such a transient. And we also notice that we have an increased, let's say, recovery time. So this peaks takes longer, or it takes longer time for the system or for the converter to recover to the previous voltage level as it was. And to understand why this is happening, we need again to look on the body plots or on the AC response. But first, let's have a look again on the simulation file. Yeah, so here we are. We can actually change here. Let's see, 0.2 amps, and then we will go to 1.2 amps. So if we run, yeah, you can see now we have a larger undershoot and a larger overshoot, and a much longer recovery time. And here we can see that the current reaches zero and stays there. So if we zoom in here, we will notice that our converter is in discontinuous conduction mode. Yeah, so it starts from zero, goes to a certain peak, goes down to zero, and stays there until a new switching period or cycle is initiated. Okay, then Let's see what's happening in the AC response. And voila, we have a huge difference. Yeah, so the green trace is actually the what we were seeing in continuous conduction mode. So it is the response, open loop response we have in continuous conduction mode with about 10 kilohertz cutoff frequency and around 60 dBs phase margin. But then, as the converter is moving in discontinuous conduction mode, then we notice that the cutoff frequency has dropped to about 880 kilohertz. So, yeah, one decade or more than one decade below. So that's a huge impact. Yeah, we noticed also that for this 880 hertz new cutoff frequency, we still have like 72 degrees of phase margin. The system is still stable. We didn't notice any. If I go back to here, you see eventually we are stable here. There is no oscillation in the output voltage, but yeah, as we noticed, the response is much slow. Okay, another point to note in this discontinuous conduction mode, we can't see the resonance peak in the open loop transfer function. Okay, so yeah, what can we do about this? So actually, what can we do is to replace the freewheeling diode with a MOSFET, and in this way we will allow the current in the output inductor to go negative. So in the end, we can have even 0 amps at the output, and the current in the inductor will swing to positive and negative values, but the average current can be 0. So if we do this, let's say if we force this continuous conduction mode state, then the transfer function of the power stage itself will not change, yeah, regardless of the load current. So then we can expect to have the same transient behavior as in continuous conduction mode for all output currents. So what I did here with this very simple structure of the gates and buffers, I simply generate two control signals, because here we have the PWM for the buck switch or MOSFET, and here we need to have the negate signal, but with some dead time in between. So we don't want to have both switches conducted at the same time, because actually we are making a short circuit across the input voltage. That means we will have a very high current peak. So in between the on time of the two switches, and that needs to be a dead time. So in this dead time, S1 and S2 are both off. So this is actually realized here with this structure. So now we have the same error amplifier, the same compensating network, and let's see what is how it's behaving. Well, now we are switching the current from 0.2 to 1.2 amps, so DCM to CCM, and back CCM to DCM. You see the current now in the inductor is allowed to go negative, so it's not clamped to 0 anymore. It goes to, I don't know, peaks are down to minus 0.2 amps, but the output voltage looks now similar to the CCM to CCM case. Yeah. So we have again about the 200 millivolt undershoot and overshoot, and we are in the position we wanted to be. So let's now have again a look on the border plots in the two cases, and let's see um, what we get. So immediately we can see again that we have again the same cutoff frequency and about the same phase margin. We can again understand that the blue trace that has a higher peak is the one valid for the zero point 0.2 amps case for the reason already mentioned. And now, well, we designed our converter on, and we how to say, calculated the output capacitance for only 1 amp change in the load current. But what if now having this synchronous rectification buck, what if we want to have a step load change from 0 amps to 2 amps and back? Let's see what's happening. So we simply adjust the simulation to let this happen. So we have 0 amps to 2 amps. This is the load current. We are with synchronous rectification because inductor current, you see, can have negative values, and we are looking for the undershoots and overshoots in the output voltage. So we can see that we are for sure over the 250 millivolt target limit. And we can really understand this because we calculated, as I said, our output capacitance based only on current change of 1 amp on 1 amp only, yeah, for the selected cutoff frequency. Therefore, what we need to do is to reconsider our value for the output capacitance. So basically, what we need to do is to double the capacitance value. Therefore, we will switch from 4 parallel capacitors as we previously had to 8 parallel capacitors. And by doing this, actually what we are doing, we are changing the resonant frequency of the LC filter. Therefore, the power stage transfer function is changed. So we need again to go through the step-by-step procedure to recalculate the components for the compensator. Yeah. So we do this. We end up here with different values in the compensator, and we are ready to see the result. So now we have again the same almost 200 millivolt undershoot and overshoot for a load change of 2 amps. So we are changing from 0 amps to 2 amps and back. And yeah, as I wrote here, we are kind of, yeah, we are back in business actually. Okay. If we look again to our small signal response, open loop response, we see that in both cases we have the same cutoff frequency, about 10 kilohertz, and we have 60 degrees or a bit higher phase margin. So we are all set. This is what we were looking for. Okay, there are some situations yeah, in which we want to check what or how much the output voltage is affected if we have a perturbation in input voltage in terms of a step, for instance. It's not really the case for our example where we said we will have a battery car, or this buck converter will be part of electronic component unit or ECU in a vehicle. But I just put it here to see how it looks like. So we were operating in a continuous conduction mode with a maximum output current, 2 amps for our converter, and I imposed a step change in input voltage from 12 volt to 8 volt and back. And I did this in 1 microsecond, which is very fast change. And I just wanted to see how this deviation looks like in the output voltage. So immediately I noticed, okay, we have like 370, 365, yeah, 370 millivolts deviation. So that's going to be above our 250 millivolt target. But here, actually increasing the output capacitance will not help. So what needs to be done here is we need a kind of a feed-forward gain or a term. It can be for this analog implementation of our buck converter, for instance, the ramp can have or can be proportional with the input voltage, and this can be, for instance, a feed-forward term that is introduced. So as long as the ramp is independent of the operating conditions of the converter itself, yeah, we will get this deviation. So what we need to do is, as I said, to lower this is we need a kind of feed-forward term, or maybe to insert an input filter, and this will simply make those very fast transients not to be that fast anymore actually. So the power stage will not see such a severe or dramatic change in the input voltage, and then eventually those undershoots and overshoot will be smaller. Okay, that's it for today. Thank you for your attention. Bye.